Hello everyone, my name is Hang and today I'm going to talk to you about binary search. After this lesson, I hope you understand the idea of divide and conquer in binary search. You will understand the implement of binary search in code and analyze the complexity of binary search. So what is binary search? It is a searching algorithm used to find element, but you have to notice that it only works in a sorted array. How can it do that? By repeatedly dividing the search interval in half. To be more clear, here is step-by-step process. First, it will find the middle index. If the middle element equal the key, it will return the index. Otherwise, if the key is smaller, it will continue searching on the left half. But if the key is larger, it will search on the right half. It will repeat this process until the element is found or the search space become empty. So I do a visualization about the process for you to easily understand this. In the step in the initial state, here we have a sorted array, and our goal is to find the key 23. The array in index go from 0 to 9, and the value are sorted in increasing order. As you can see, this is important because binary search only work on sorted data. At this point, the search range is entire array. So we have step 1, which compare with the first middle element. We set low equal to 0 and high equal to the index 9. We compute the middle index, which is 4, and the value of index 4 is 16. Now we compare 16 to our target 23, which is greater than 16. The target cannot be in the left half, so we eliminate the entire left portion and move the search space to the right half of the array. Finish step 1, we will continue with step 2. In this step, the new search range is low equal to 5 and high equal to 9. We calculate the new middle index, which is 7, and the value is 56, right? Now we compare again. Is 23 greater or smaller than 56? Well, it's smaller, so the target must be in the left part of the sub-array. So we eliminate the right portion and move the search space to the left. Now the search range become no equal to 5 and high equal to 6. We compute the new middle, which is 5, and the value is 23, which exactly matches our key. Therefore, we have successfully found the target, and binary search stop here. Okay, so now I'm gonna show you my code of binary search. Let's define a function called binary search with two input array and target. And we set two pointer. Left start at the beginning of the array and right start at the end. We continue searching as long as the left pointer has not passed the right pointer. If left become greater than right, it means the target doesn't exist. And here we calculate the middle index using integer divisions. This middle position is where we compare the value of our target. And if the middle element matches the target, we immediately return the index. That means we successfully found the value. If the middle element is smaller than the target, then the target must somewhere on the right side of the array. So we move the left to the mid plus 1 to discard the entire left half. If the middle element is greater than the target, then then the target must be on the left side. So we move right to the mid minus 1 to discard the right half. If the loop finished and we still haven't found the target, we return -1 to indicate that the value is not in the array. So now let's look at this example. Array 1, we have 2, 4, 5, 6, 7, 8, 9, 10, 12, 13, and 14. And our target is 12. Okay, let's say 12. In this example, the target is 12, so the binary search will check the middle, then narrow the range a few times, and finally return the index where 12 is located. So now let's print the result. Okay, wait a second. Oh, here I just got a mistake, so let me fix that. We will choose the current file, and yeah, the output is 8, so it is the current output. So let's talk about time complexity of binary search. Let's start with the best case. The best case for binary search happens when the target element is located exactly in the middle of the array during first comparisons. As you can see in this example, the target is 5 and the middle element is 5. We perfectly match the target. So in this situation, by research only lead one comparisons. That's why the best case time complexity is 0.1. Let's see the average case. Now in real situation, we usually don't know where the target is, right? So by research work by having the average at each step, would give us a logarithmic complexity. As you can see, every time we make a comparison by research, cut the remaining search space in half. So after just a few comparisons, we are left with a very small portion of the array, as you can see in the example. So on average, the number of comparisons grow like O log 2n, which means average case time complexity of binary search is O log n. Finally, we have the worst case. Binary search worst case happen when the target is either at the first element, at the last element, or not present in the array at all. As you can see in this example, even the worst scenario by research still divide the array by half each time. That means the maximum number of comparisons still log 2n. So the worst case time complexity also remain O log n.
Good evening, everyone. Today I'm going to present the algorithm design and sorting algorithm part. To be more specific, it is quicksort. After my presentation, you're going to be able to understand the divide and conquer paradigm in quicksort, implement quicksort algorithm, analyze time complexity, and identify avoid common pitfalls. So, to be more specific, quicksort algorithm is a comparison-based algorithm which is widely used in real-world system. It is a recursive algorithm with time complexity is big O n log n for average cases and big O n square for worst case. This sorting algorithm is based on divide and conquer. There are three main steps in the algorithm. First of all, you're gonna choose the pivot. It can vary. You can choose the first element, last, or random, or the median of the list. Secondly, is partition the array, which means that you're gonna rearrange the array around the pivot. All the elements smaller will be on the left and greater on the right. Recursively call, you're gonna recursively apply the same process, which is the partitioning the array to the subarrays. And it's gonna recursively call until it meets the base case. This is the visualization part. Okay, to make it easier to understand, I'm gonna show you guys the visualization of it. Okay, so I'm gonna show you guys the live code. This is the first example, which is a basic quick sort implementation. First of all, let's define function. Array. And then if this is the base case, smaller or greater than 1, which is the base case. Please remember this or else. Next, we're gonna create this one. With left is a list. X for X in array if, oops, sorry, this is smaller, this is equal to, and then the right is a list that you're gonna store X in the array, which is larger. Remember the slide that I showed you just right now? Okay, so you guys gonna create a list. This is the pivot. Actually, I'm choosing the median. So, I mean, you can possibly choose any number in the list that you want. It is varied. And then left is a list that's smaller than the pivot. And then the middle is if it's equal. And then right is larger than. Okay, so I'm gonna return recursively call it left, middle part, and then right. Let R is a list of 64, 34, 25, 36, 12, 20, 11, 19. Let's say. Okay, so let's print quick sort R. Okay. Okay, we have a perfect sorted list. There are two more examples. If you want to see, I'm gonna put it right here. Finally, is common mistakes. With the first mistake is you guys forgetting the base case. With no base case here, it's gonna lead to infinite recursion. So we should have the base case, which is the length of the array with smaller or equal to 1. The second mistake is you guys not handling duplicate properly. You can see here, if you put the equals here to the list right, then it's gonna include the duplicate. You should create a middle list and then for the equal part separately here, so it's not face the duplicate mistakes. The third mistake is not really a mistake, it's like, a bad choice, is you guys put the first element in the sorted array is the pivot. So the worst case is gonna result in the time complexity big O(n) square. So instead you should random. You should random pivot or the median. It's gonna result in a average performance, average time complexity, which is smaller than the worst case. So the fourth mistake is the index out of bounds in in-place sort. You can see here that the code is like the -1 and +1. So it's gonna result in the out of bounds because this is the index in Python, You have two minus and +1. Okay, so finally the fifth mistake is modifying original array unintentionally. It's like if you want to preserve the original list, then if you put the original list right here without copying it, it's gonna modify your original list, so it's quite dangerous for in some cases. Instead, you should create a copy of the list and then put the copy in the algorithm, and then it's only sort the copy one, and then you can have the sorted and the original list instead of you modify the original one.
So next we'll be discussing class, object, and encapsulation. By the end of this lesson, you will be able to understand four key concepts. First is the relationship between object and class. Second is the role of the constructor, attributes, and methods. Third, is the concept of encapsulation. And finally, you'll be able to understand how to use the set and get method. So before we define them, let's look at why we use them. Why OOP? There are four main reasons. First, it helps us organize code and group related data and behavior. Second, it allows us to reuse code, meaning we can create many objects from one class. Third, it makes our programs easier to scale and maintain. And last but not least, it supports the core OOP principles, the abstraction, encapsulation, inheritance, and polymorphism. So let's start with the class. What is the class? Well, it is essentially a like a blueprint or template for creating objects. Inside a class, we define attributes, which represent data, and methods, which represent behavior. Basically, the class describes what an object should have and should do. The example we will use for this concept is the class car. So just imagine the class car as the definition, and from that we can generate multiple objects. So if the class is the blueprint, so what is an object? An object is an instance of a class, while the class is just the template. The object contains actual data stored in attributes. The object is also what can use the class methods. So here's a specific example. So as you can see, my car equal to car and Toyota Camry 2020. So in this line, we are creating a specific instance, an object from the car class. So now let's look at the structure of how we create this. So we use a constructor. Uh, there are four things you need to know about the structure. So first, uh, you can see it will have like this kind of form like def in it. And you will see the keyword self, which refers to the instances. The and also the attributes are variables that hold information on each object. And crucially, each object had its own copy of the attributes. So moving on to our next major concept, encapsulation. Encapsulation is the practice of hiding internal details to protect data from unwanted access. It effectively controls how data is accessed and modified. Usually, encapsulation happens during the initialization of attributes. When we do this, attributes can be public, protected, or private. So, to help with encapsulation, we use get and set methods. So first, what is a method? A method is simply is a function but with a like smaller scope. So why use get and set methods? So we use them for three safety reasons. So first, it prevents direct modification of important variables. Second, it keeps data safe from accidental or invalid changes. And third, it ensures internal state is always valid. So that covers the core concept of four of our lesson on class, object, and encapsulation. Next, you will see life code from Phương to better understand the concept.
The first thing you're introduced to when you get into the Pokemon world is the Pokédex.
Pikachu, the mouse Pokemon, and the evolved form of Pichu. Pikachu's tail is sometimes struck by lightning.
From what we just saw, we can consider the Pokédex is a class because it provides a structure for each Pokemon. A Pokemon could be the instance of the Pokédex, and the attributes are the name, the type, and the species of each Pokemon. So we can conclude that the class that we can have is the Pokédex, and the instances later on are each of the individual Pokemons because they have the same structure of information returned: the name, the type, and the species.
It's live code time.
First, I create the class using the class keyword and name it Pokédex. Pokédex should be capitalized for naming conventions. Then I make the constructor. You define it like a function, but inside a class, using init with dunder. And then I put the parameters, name, species, type, and health. And then I initialize them with the self keyword referring to the instances that we later create. Here, I am protecting the attribute health using 1_. Later, we'll see more ways to encapsulate attributes. The constructor allows you to construct your object instances of the class. You pass in arguments according to the parameters you set when you initialized it. Let's get to the code. Here we use the constructor we've already built. So we name Pikachu, and then we input the values that we put in the constructor, the name, the species, type, and the health points. This is how you make a new instance using the constructor that you've built. And another practice for Charmander. Keep in mind you use Pokédex instead of init.
It's live code time.
As you can see right here, the attribute health is encapsulated with 1_, which means it's protected, not private or public, which means other programmers can't access it outside of the class right here. So now if you double underscore it, it's private and other programmers can't directly access it outside of the class. So they make a get function, a get method, which returns the method securely, allows other programmers. Next up, I want to make a string function to output the data, because right now if we print Pikachu and Charmander, it would return the object location, the memory address of the objects. So I'd have to define dunder string because this is a special method. So I'd want to return an f string formatted. So I want the name, Pikachu, and then the species, Pokemon is lightning type, so type self.type is type and has, and then to call health points. So now you print it, you get the formatted version. And if I want to format this correctly, I'll make this a title and lower everything, lower. Yep, there we go.
So, hello everyone, I am Win Ang, and to expand more on object-oriented programming, I will be covering inheritance, polymorphism, and abstraction. So, first, think of Spider-Man. He inherits all the basic human traits from his parents, like hands, legs, walking, but after being bitten by a spider, he develops new traits like shooting webs or climbing walls, and this is exactly how inheritance works in OOP. So the child class derives from a parent class and it reuses the attributes and methods of the parent class. However, it can ask customizations and different attributes of its own. And here you can see that we have a couple different types of inheritance, including single, hierarchical, multi-level, and some more. And I will be demonstrating these. First, I'll create a human class. The important thing here is that this class is a foundation because I don't want to rewrite this code every time I create a new type of human. Now I create Spider-Man, and it says human, which means that Spider-Man inherits from human. And I will run it really quick. This is single inheritance, one child, one parent. I'll add another layer called superhero. So instead of inheriting directly from human, Spider-Man inherits from superhero. So now Spider-Man has human, superhero, and Spider-Man specific abilities. This is multi-level inheritance. Now I'll add Iron Man. Iron Man and Spider-Man both inherit from superhero. They share the same base behavior, but each has their own unique abilities. This is hierarchical inheritance. This means that if I ever need to change how all superheroes behave, I only change it in one place. Now, think of pho, which I'm sure we all love, and you might know that northern and southern pho are both pho, but they taste vastly different, and you might have a preference for either one. And this is how polymorphism works in OOP. It basically means objects of different classes responding to the same method called differently. This allows for flexible system design and encourage loose coupling so that if there are any errors, it will be easier to fix. And for this specific presentation, I will be focusing on method overriding. Here I'll create a base class called pho, which represents the generic idea of pho. This is a common interface. Now I create two subclasses, and they both override the same method, getFlavor from pho. The method name is the same, but the behavior is different, which is called method overriding. Here I will call it, and here's where polymorphism actually happens. I don't check if it's north or south, I just call getFlavor, and Python knows which version to run based on the object type. This makes code flexible and easy to extend. If I add a new type of pho, this loop still works. Finally, abstraction, which is pretty straightforward. This is basically hiding complex details while showing only what is essential to the user. And in Python, this is done using abstract-based classes. Here, I'll create an abstract class called shape, which sets the rules for every shape. If I try to create a shape directly, it will not work because the methods aren't implemented, which is how abstraction works. It tells us what methods are required only. And now to further demonstrate abstraction, I will just paste the rest of the code because, well, you don't need to know what they are. That's the point of abstraction. You only need to know the necessary. And now I will just run it and you'll see that it works. You can see how it is passed on.